All right, we're going to be starting part 2 of lesson 1.3, transformations of functions. We're starting this section talking about a difference between two types of transformations that we have. So there's things that are called rigid transformations and things that are called non-rigid transformations. The two transformations we discussed in part 1 were both rigid. So a rigid transformation does not change the basic shape of the graph. It only changes its position by shifting or reflecting. There's another rigid transformation, rotations, which we didn't do in that and we're not really going to do. But that would fit into the category of rigid. If we rotated it, it would still just sort of change its position. This part is going to be talking about a type of non-rigid transformation called a stretch or a shrink. So we're going to be looking at a stretch or a shrink. So our transformations are really only going to focus on vertical stretches or shrinks. We could also think about horizontal as well. And later on, when we start graphing trig functions, we will kind of start discussing some horizontal stretches or shrinks that can occur. But right now, we're just going to focus on vertical. So a vertical stretch by a factor of c is written in this way. We multiply c, a constant, times our function. It's caused a stretch when c is greater than 1. A vertical shrink by a factor of c is when we multiply the function by c, but c is between 0 and 1. So we could have a fraction or a decimal or something that was between 0 and 1. So for example, we could have like 1/2 of f of x. This would cause a vertical shrink by squashing the graph down to be kind of half as tall, someone might say. Another thing here, factor of c, this can be a little confusing because it's not shrinking it by a factor of half. That's sort of like a double negative. Some people would say if you have a 1/2 inside, it would actually shrink by a factor of 2. It's 2 times shorter, 2 times less tall than it was before. We'll kind of use both interchangeably a little bit. I like just referencing whatever the multiplier is and just using that, but either one is okay. All right, so let's go ahead and just go ahead and straight look at some examples of this. I think it will make more sense there. Okay, yeah, all right, so here we go. We have the absolute value graph. So the red one here, this is gonna be our kind of original, it's not the plain parent function for absolute value. It is shifted down a little bit, and that's our red graph that you can see here. I'm just going to focus on a couple points and kind of what happens to those few points. So let's just say we'll do that one, and we will do one over here. We'll do, I don't know, this point. Let's kind of look at where those points go in terms of the stretches that we're dealing with. All right, so now I want to focus on this one right here. This one is a stretch because we're multiplying by a number that's greater than 1. We're stretching by a factor of 2. So what happens when we do a vertical stretch is it always comes from the x-axis. So right now, our original function is 4 units away from the x-axis, right? This goes from 0 to -4. When we multiply by 2, we're going to be doubling that distance. So now, instead of being 4 units away, we're all the way down here. We're actually 8 units away. So that doubled the distance, hence multiplying by 2, stretching by 2. So when we can also see that taking place right here at the other point we indicated. Right here, we're currently 2 units away. Above the axis this time, but the same thing is happening. We're kind of stretching from the top and the bottom. It's like you grabbed it on both sides and stretched it. And now this point is double that distance away. It used to be 2 units away. Now it's up here and it's 4 units away. So the distance, every point is doubling its distance away from the x-axis. Now, that does leave one situation. This point right here and its pair on the other side, these points don't go anywhere because they're currently 0 units away. They're on the axis. And so if we multiply that distance, we double that distance, doubling 0 is still 0. So these points remain fixed. So any x-intercepts will always remain fixed when we're doing a vertical stretch. X-intercepts will remain the same. So this first one is our vertical stretch. I'm going to erase some of these things here. I'll just leave them up there. Doesn't really matter. The next one we're dealing with is right here. Now we're multiplying our function by a 1/4. So this is a shrink because that number is between 0 and 1. We're going to be shrinking by 1/4. So now instead of increasing the distance from the x-axis, we're going to be decreasing the distance from the x-axis. All of our points are now going to be 1/4 of the original distance from the x-axis. And we can start by, let's just go ahead and look at that first point we looked at last time. Right down here, we're at -4. That's 4 units away. And the new graph is at 1. It's only 1 unit away. That is 1/4 of the overall distance that it was originally. That's where we're seeing that 1/4, and it's shrinking. Shrink is a little weird. It's more like kind of squashing down or scrunching, but that's the word we're going to be using, is a shrink. So again, it was 4 units away. Now it's 1/4 of that distance. It's 1 unit away. Same can be thought of here. It's a little bit harder to see because we're not dealing with whole numbers, but this is 2 units away, and this one looks like it's right at a half. So that would be 1/4 of 2. Right? If you do 2 times a 4th, you're going to get 2/4, which is a half. And that's where this graph is at. It's at 1/2 right there, 1/4 of that distance away. But again, the x-intercepts remain the same, because if they're 0 units away, if we change that by a factor, multiply it by a 4th, it still would remain 0 units away. A lot going on there. I kind of wanted to show you visually what's happening with the graph and how the stretch or the shrink is occurring, either getting closer to the x-axis on a shrink or stretching farther away on a stretch. All right. Here's another example of that, and we can kind of quickly look at it. The red one is our original right down here. I'm going to focus on the vertex really, but we can also see the x-intercepts remained constant. 1/3. So our original graph was down here at -6. It was 6 units away from the axis. And then that distance is decreasing. It's down here, it's only here at -2. So it shrunk, it got closer to the axis. And that factor is right here, 1/3. 2 units is 1/3 of 6 units. So it is now 1/3 of the distance away from the x-axis. And we could look at that being true at other points as well, like here and here. This point, which was 3 units away, is now only 1/3 of that distance away. It's only 1 unit from the axis. Okay. All right, let's go ahead and do this again with just the equation rather than kind of examining the graph. So we have our function, g of x is equal to 1/2 of x squared. That's a quadratic. We'll go ahead and name our quadratic function right there. How has this graph been vertically stretched or vertically shrunk? Well, in this case, we're dealing with a shrink because our c value is between 0 and 1, right? It's in there, it's in between 0 and 1, a half would fit in there. So this is a shrink. We're going to shrink by a factor of 1/2. Now again, we can also write g of x in terms of the parent function f of x as well. We could say that g of x is equal to 1/2 times f of x. For a shrink, or a stretch, we're just multiplying the original function by a value. All right, let's go ahead and move on to another example. Okay, so we have g of x is 4 times the absolute value of x minus 5. So this is obviously an absolute value as our parent function. And the stretch that we're dealing with is this one. Obviously, this is a shift to the right. 5, but I'm only really focusing on the stretch or shrink right now. This one is going to be a stretch because our C is greater than 1. It's actually a 4. So we are stretching by a factor of 4. So all of our points would now be 4 times farther from the x-axis. I'll go ahead and write g of x in terms of f of x as well. So it's 4 times f of x, but we're also doing that minus 5 on the inside. So it'll be x minus 5 on the inside there. And that's how we would write our function g of x in terms of the parent function for absolute values. All right, I'm going to clear that and move on to our another example here, talking about the sequence of transformations. A lot of times it's important to know what order these transformations take place in, because if we change the order up, it's going to actually affect what the graph would look like. So, and there is a right order most of the time. So here we have our function, parent function, the square root of x, and we want to look at what's happening to it. So in this example, there are a few things happening. We have a negative in front, which is a reflection over the x-axis. We have this plus 4 on the inside, which is actually moving it to the left 4. And we have this minus 2, which is actually moving down 2. So those are the 3 transformations that are taking place. And we kind of want to think about, does it matter the order? Could we do these in any order and just sort of end up in the same spot? Sometimes we can, sometimes it doesn't matter. Like if we just had some translations here, it wouldn't matter. We could go 4 to the left and then 2 down, or we could go 2 down and 4 to the left, and it just doesn't matter. We'd end up in the same spot. But because we have this reflection in here as well, it will matter, because it matters if I move down and then reflect, or if I reflect and then move down, we'll end up in different spots. And that's because these are sort of, these two things are kind of moving the same. They're both vertical movements. Reflection is going up and down here in this case, and this movement up and down. So they kind of interfere with each other, you might say. What I like to do is I like to just kind of look at my function and determine the order of operations. What's happening to my variable? What would happen first? So my first thing in this case is going to be left 4. That's happening the very first thing on the inside. Then what would happen is we take the square root, but that's just our parent function. That doesn't actually do anything in terms of a movement. The next thing is we would apply this negative, which caused the reflection. So we reflect over the x-axis. And then the final thing, the very last thing we would do is this minus 2, causing it to shift down 2. So that would be the proper order here, again, based on how we would evaluate this using our order of operations. All right, I'm going to clear these off and move on to the next one. All right, so we'll do 2 more examples of this based on the order that they would happen. Okay, so we have a parent function, absolute value of x, and our other parent function, cubic. We want to look at what's happening to it. So there's 3 things I see. There's a 1/2, there's a negative, there's a minus 3. Again, so that represents 3 different transformations. I want to think about the order that these things are happening. Now, I could look at my 2 graphs, kind of compare them and figure out the 3 things that are happening in the order that kind of achieves the right graph. But right now, I'm just going to think about order of operations. On the inside, that's the very first thing that would happen. I'd apply this negative. That causes a reflection over the y-axis this time. This is a kind of a funny one in this case, because if we think about what's happening here with absolute value always turns everything positive. So this negative, this transformation in general is having no effect, but it would be the first thing that would happen. Then the next thing we would do after we take absolute value is multiply by 1/2. So there's now a shrink by 1/2. So everything's getting shrunk down closer to the x-axis. And then the final thing that's happening is we're going down. That would be the last thing we do when we're evaluating that function. All right, we'll do this one here as well. There's 3 things I'm noticing that changes from this cubic function. And so that's going to cause 3 transformations. We need to look at what they are. So looking at it here, I see first there is on the inside, the very first thing I would do when I put in something for x would be to add 1, which is actually a movement of the left to the left of 1. Then I would cube it, which is just our regular parent function, so that's nothing. Then there's a stretch. That multiplication by 3 represents a stretch by a factor of 3. Everything's getting pulled from the axis. And then finally, plus 4 on the end, that's actually going to be moving the graph up 4. And we could take a look at these graphs on Desmos and kind of sort it out ourselves that way in terms of what would achieve the right graph. All right, I'm going to go ahead and clear these. Okay, last thing that I want to do here is I want to think about if I have a function that's kind of a starting function, and then I have a transformation that's being written in terms of that function f, what I want to be able to do is actually write out what that resulting equation would look like. So I'm going to go ahead and do that. It's a little complicated. I got to think about this. So the way I'm going to start is kind of on the inside here. I'm going to write that part out. So that would be negative. Now instead of x, right, we're putting in x minus 4. So it's going to be x minus 4 plus 1 squared. So that's this piece. Now I'm supposed to multiply that function by 1/3. That's taking care of this piece. And then I'm supposed to add 10 to the end of that. So now I've kind of got everything in there, and I want to just do a little simplifying. Well, the negative and the 1/3, I can actually just put those together. Now on the inside here, I can actually combine some like terms. I have -4 and plus 1, so that's going to be -3 plus 10. So now I've kind of put it together, and I like it in this form to leave it like this, because this shows me if we're actually going to compare both of these to just a regular quadratic function, this kind of shows me the differences between them, right? This one had a shrink of 1/3 and moving it up. Yeah, so it kind of, I can compare them both now in this format there. But I could take this further, like I could square it and multiply everything out. But if I want to compare them in terms of their transformations to the regular parent function, I could just go ahead and stop right there, which is what I'll do. All right, hopefully we found all of this helpful. One final thing I want to do is just kind of take a look here at this one and mostly kind of walk through that input process again of inputting something in for the variable, because this one has 2 instances of it, and so a lot going on with that. All right, so again, what I'm doing is I'm putting in -x plus 2 into my function. So it's going to be 4, and I'm giving myself a lot of space here. So that's the first part. And then I do need to multiply this whole function by 2. And then I need to subtract 3 onto the end of it. This is pretty messy. I could just go ahead and use this equation if I wanted to, if I was like trying to graph it on Desmos or something. I could also do some multiplying things out and get from there. Right now, I'm just going to stop with it here because I'm not going to gain much by kind of simplifying this one out. All right. Let's go ahead and stop right there. Try the homework for 1.3. We've already done a lot of writing in terms of a parent function, so I'm going to leave these for you guys to kind of look at if you want to try some other examples. Make sure to do the homework, and one of the problems I want you to turn in on Google Classroom, so you'll find that assignment there. All right, guys, good luck. Let me know if you have questions.